and letting me know about his lecture series. So thank you very much again for this invitation. So I have scanned some handwritten notes, maybe somewhat similar to Süleyman Hoca's notes. I will share them with you. Probably I have the right to share. So let me just put it up first. So I think you can see my PDF file, right? In view.
You can see it.
Okay, great. So here is the idea. If I make this too big, this is not good. Let's have some view here. So this is Ito Calculus lecture series. I guess this is the 5th lecture. And I think it's going to bring the whole semester to a reasonable point to stop at. If you like to continue learning, I think it's a good point to stop and yeah, start your new learning journey right after. Now, okay, I wonder if in the audience there are some mathematicians as well, in addition to engineers. I know Siam is applied mathematics student chapter now. So maybe some things will be unnecessary for you, some of the definitions and so on. Then you should just bear with me. Okay, I apologize at the first place. But otherwise, it's sometimes good to go over some basic definitions. So that helps remembering everything together. Only if you're a math student who has just graduated, these may be somewhat a view of what you have done over the curriculum. Okay, what do we have over the curriculum? First of all engineers and science students take calculus plus linear algebra, right? Okay, so in this case, everybody knows vector spaces, especially from real lines, right? Rn in general, in n-dimensional real space. But if we want to define vector space more formally or in a more abstract way, we want to think of a set V along with addition and scalar multiplication, and scalars coming from R, for example. But in general, we call a set which will supply the scalars. We just call them, but we want that set to be a field. So the definition of field comes from algebra, but this is basically real line or complex numbers for us, real numbers or complex numbers for us, where you can do addition, subtraction, and so on. So we already have such a set, real numbers, that we can pick our scalars from. Okay, what about the set V, which is the vector space? We want to think of those vectors very abstract manner, as long as we can add them. And we can multiply with real numbers or complex numbers for the purposes of our description here, okay? Now, before we go on with this very basic definition, I want to give you an idea of what we're going to discuss today. Today, we're going to discuss Hilbert spaces. So our title today includes closed vector subspaces, orthogonal projections and complements, and we want to talk about some L2 spaces as relevant to us, okay? What are they? We're going to see very soon. So assuming once again, we have engineers in the audience, and we want to make this, of course, open to all science students and engineering students, as well as mathematics students. We want to talk about some basic notions. A metric space is something you have, I'm sure, encountered around, even if you haven't maybe defined it that way in your courses. So a metric space is a set M along with a metric or distance function. And that distance function measures the distance between 2 points of that set. And when you measure it, of course, think about measure in general, it has to be positive. And I know you have been doing measure theory up to this moment with Professor Üstüner for a long time, but that idea already comes from a metric space where we want to measure things, right? So anyways, that's why a measure is positive in general. If you're not talking about signed measures, generalize it and so on. But similarly, a distance function should be positive. We want to measure the distance between 2 points of a set. Now, a set would be called a vector space if between the elements of that set or points of that set, we have an addition defined as well as scalar multiplication defined, of course, with some properties. So formal definitions of these, you might look at this reference, for example, or any real analysis textbook, okay? So the first reference is Introductory Functional Analysis with Applications, where you can find more about Hilbert spaces. In any real analysis textbook, you could find everything related to metric spaces. But vector spaces are the fundamental instruments that we're going to use in function analysis, which includes Hilbert spaces today. Okay, so yeah, linear algebra. All students here took, I think, in their first year or second year in university education, vector space definition in their calculus, one of the calculus courses, linear algebra, okay? Maybe that particular introductory math course was called linear algebra or calculus 2, whatever the name was. You have learned matrices, you have learned vectors, you have learned dot products in Rn and so on, right? Everybody somehow remembers somewhat inner product, maybe not, but the dot product of two vectors you have seen in physics courses, in introductory math courses, and so on. But the metric space, although distance is very, very intuitive, maybe you haven't seen formally. Anyways, so formal definitions are assumed to be at the background, but I will remind you some necessary definitions as well. All right, when I have a vector space, I can put some more formalism or more structure to it. And that structure, for example, could be inner product. So inner product is a function defined on V times V, meaning two elements of V, the vector space I have there, two real numbers or complex numbers, okay, which I call set of scalars actually. Remember? V along with scalar multiplication, where I make sure scalars are coming from a set, real numbers in general, or complex numbers in general, okay? So inner product is something defined between two elements of that vector space. And that will look very, very familiar to you because I will give you some examples. So dot product is an example in Rn. So here are the definitive properties of inner product function. So it is shown with those like less than, greater than type angular notation. X plus y is a vector. Remember, if I add two vectors, it's another vector in the same space. It is closed under addition, right? V is a vector space. So if I multiply the vector x plus y, not multiply, but take the inner product of x plus y with z, this is the same thing as some sort of a distributive property here. X and z can be considered for the inner product, which gives a real number, plus y and z, inner product of y and z, which is another real number, add them. This is the same thing as taking the inner product of the vector x plus y and z. Okay, this is the first property. Alpha is a scalar. Multiply the scalar with the vector. Alpha x is another vector. Remember, a vector space is closed under scalar multiplication. So alpha x is another vector. Inner product of alpha x and y, alpha can be taken out. So x and y inner product, which is a real number, multiplied with alpha is also a real number. They're both scalars. Multiplication is defined, perfectly fine. Real number on the left-hand side, real number on the right-hand side, okay? Now, these properties will make best sense if you consider an example. So we can put some examples on top, but look at the following. Inner product of x and y, the commutativeness is not there, commutative property. It is commutative only if you add a conjugate. So complex conjugate, what is it? Eşlenik, right? Of the imaginary number. Here, that's shown with the over bar there. In general, inner product of x with itself is positive number. However, if the inner product of x with itself is 0, this will force x to be 0. No other vector, if it has 0 inner product with itself, can be 0. Okay, so it will not yield 0 inner product if it is not 0 itself. All right, now I will give some examples, but shall we remember dot product? Can you now imagine x and y vectors? Okay, dot product of, shall we do one example? Just to warm up. I know maybe it is too boring and too simple. You will let me know. Okay, the participants should let me know. Otherwise, I do sometimes give very simple examples. But let me see if I have an annotation here. Little bit of annotation. Okay. Can I do annotate, write on some notation on top? Maybe I don't have any possibility like that. Okay. Okay, I don't think I have annotation ability. From the Zoom, I could have it, but I couldn't find. Okay, that's fine. Well, anyways, that's what I'm saying. I cannot write on the screen. I don't have a pen and I don't have that facility. And for some reason, Zoom will not let me do it electronically. So maybe we will just be talking on what I have written here. So can you take the dot product of a vector 1, 2 in R squared, R2, okay, with 3 and -4, right? So x1, x2, y1, y2. How do you take the inner dot product? x1, y1 plus x2, y2, right? Row vector, column vector. You can just take the dot product. You know how to multiply that, right? Row vector times column vector will give you a single number. Okay, if you multiply two vectors like that. Okay, so basically we're talking about vectors. Always imagine R2. And if you take the inner product, basically this is a dot product in R2, right? x1, y1 plus x2, y2, if I'm talking about x vector and y vector, for example. Okay, in any case, here is when it becomes something concrete and reasonable. Now, norm of a vector. How big is a vector? It is the square root of the inner product. Now, if you define norm with this fashion using the inner product definition, this defines a norm. Remember, inner product of x with itself is positive, therefore you can take the square root. And you can define a metric with this norm, because norm is like a distance. So triangle inequality holds, therefore metric and norm are some notions you have, I'm sure, ran into in your physics courses and so on, if you haven't seen it in a math course. Okay, now if V is an inner product space, what do I see? Because of the inner product, I can talk about a norm like this. But norm is too close to a metric. We can talk in a moment about some examples. So in Rn, dot product is an inner product. If it is the inner product, you can also talk about some distances. So think in terms of a vector x with elements x1 and x2. What is the inner product of x with itself? x1 squared plus x2 squared. If you take the square root, this is Euclidean distance. Square root of x1 squared plus x2 squared. That's the Euclidean distance in R2. Well, that distance is also a norm in this case. And without talking about the axioms of norm, you can just assume that it's very close to a metric. Well, metrics will be used here. Consider this second, maybe more unusual example. We talk about some functions, okay, and the set of those functions which have finite integral of their square will be called L2AB. Okay, what type of integral am I talking about? Well, if you consider just your ordinary Riemann integral, that's fine, but basically it comes from measure theory where dt corresponds to the Lebesgue integral here. So whatever you understand from integration, that's no big deal. But I want to think of those functions for which a to b integral of xt squared is finite. So if you take the square root of that I'm going to call the norm of that function. And this is just a visualization, like a signal for engineering students. Okay, a signal x of t of time. Now, from a to b, I want to think of a finite interval, for example. It doesn't have to be, but in general, I want to consider those functions in this set. L2AB denotes the set of those functions, x. Now, the inner product is defined as x of t, y of t dt integral, right? And so what I'm talking about is there are two functions over AB, and I want to take the inner product. Well, this satisfies the axioms of an inner product. Remember, what were the axioms or what were the definitive properties of inner product? 1, 2, 3, 4 axioms here. Now you can show that with this definition of an inner product, x and y being vectors, okay, they also satisfy the axioms of being vectors. They can be added, two functions can be added, they can be multiplied with scalars and so on, and they're still closed under such scalar multiplication, function of space of functions. So basically x and y being functions, as you may see here, are vectors. Inner product is defined. What else? With this inner product, I can define the norm. And with that norm, I can define a distance function for my metric space. I want to think of this function space as also a metric space because I can measure the distance between two functions. What is the distance between two functions, x and y? It is norm of the difference of those functions. And if I consider the definition of the norm of the difference, it is x of t minus y of t squared, the integral of that from a to b, and take the square root. That will give me the distance of those two functions. Agreed? So this is a very typical way of applying our main ideas, which actually originate from real line or R2 or Rn, right? We can all understand vectors in real numbers as vectors, or R2 in the plane, or R3 in three-dimensional space, their distances, and so on, that we have learned in elementary or introductory courses. But now our vectors are functions, and the distances, the inner products, and so on are generalization of dot product in Rn. So, okay, so maybe this will be our basic example to understand all the abstract looking new definitions we will have in this lecture. Okay, any question here? So far, so good. Just look at the differences of these two functions here, right? Square them, that becomes positive. Take the integral from a to b, that will give me a complete, or let me say aggregate idea of the distance in a positive manner. And if I take the square root of that positive number, well, I will come back to the units of x or y. And yeah, that distance can be measured with a distance function d, or something I call a metric. D is a metric. Okay. Now, why do I make a distinction of these? Because there are some definitions we're going to learn today related to metric spaces, in addition to some definitions we're going to learn related to vector spaces. So we will work with some function sets of functions, which we may see as a vector space or a metric space, because related notions we're going to apply. Okay, what are we going to first talk about? Completeness. Well, completeness is about a metric space, M, if it is called complete, if every Cauchy sequence in M converges in M. Okay, that's something you will remember very well, Cauchy sequences. I think you should remember from calculus, but let me rewind. Xn is Cauchy if for large n and m, xn minus xm will be less than epsilon for every epsilon, right? I can find such large n and m for a sequence x, x sub n, x sub m are elements of that sequence. So in real numbers, when you consider such sequences, well, they always converge. If two elements of a sequence become very close to each other, it will converge to a point in the real line. But if you remember rational numbers, it's not complete because there are some limit points of rational numbers which are not rational. So some sequences of rational numbers will converge to a limit which will be irrational. And irrational numbers are not part of rational, so they will be real numbers. Therefore, this is a pretty trivial example that you might have encountered in your calculus courses related to Cauchy sequences, but maybe you have not talked about completeness at that time. Well, if a space is complete, we're talking about all Cauchy sequences converging in that set. Now, in general, a given inner product space is not complete. So if I have a Cauchy sequence in an inner product space with all these inner product axioms in place, Normally, Cauchy sequences don't have to converge. When I'm talking about convergence, what am I talking about? I'm talking about distance of 2 points or 2 vectors of a sequence of vectors is converging to 0, right? All right. So that converging to 0 means it's Cauchy, xn and xm, the distance converging to 0, that becomes a Cauchy sequence, of course. But convergence, what does that mean? Distance of xn to a point x is becoming 0 as n goes to infinity. Okay, now then I would call x to be the limit of xn, that sequence. So you can see the interplay of convergence, which is a metric definition, the distance of the elements of a sequence to a point is becoming 0 as n goes to infinity. That's convergence of elements in a metric space. On the other hand, completeness is an addition which says every Cauchy sequence in M converges. All right. Now I'm coming back to a vector space where I have inner product space. In general, this doesn't have to be complete. Maybe Cauchy sequences will not converge. However, there is a big theory behind this. A theorem called completion theorem will tell us that a given inner product space can be completed. So this inner product, extra inner product structure is very helpful. The theorem says for any inner product space X, there exists a Hilbert space H and an isomorphism from X onto a dense subspace of H, and H is unique up to isomorphisms. Now there's so many new terminology here for maybe undergraduate students here, but this is just for the sake of being complete as well. I gave the whole description of the theorem or statement of the theorem, which you might like to study from the references I gave you. But if I translate it to simple terms, first of all, Hilbert space is a complete inner product space. So it's an inner product space where I have defined inner product. Also, it is complete in the sense of as a metric space, the Cauchy sequences will converge to an element in that set. Okay, so I'm talking about a set. It's a vector space with the inner product. It's an inner product space. The distance function is defined using the inner product. And Cauchy sequences, convergence of Cauchy sequences now makes sense to me. What about convergence? Well, the distance between two elements or the sequence of elements and a final element is becoming 0. So convergence is also defined. And in Hilbert spaces like that, complete Cauchy sequences converge. If I have such an inner product space, I'm going to call it a Hilbert space. So from now on, please remember, Hilbert space is a complete inner product space. Okay. Now the theorem says, if somebody gives me an inner product space, I can actually complete it to a Hilbert space. So basically completion, well, there's a lot of theory behind that. Maybe I cannot make this any more intuitive, but you know what? I want to talk about an inner product space which is completed, by this theorem. It's a constructive proof. The proof of this theorem is very constructive. I know how to complete an inner product space. From now on, I can work with the completed version of that inner product space, or they would just give me the Hilbert space there right away. For example, if they give me real line, real numbers, it's a complete vector space with the inner product, dot product. or okay, what do you call a scalar product or dot product, right? Okay, well, in R, it's just ordinary multiplication, isn't it? Okay, so far so good. I have repeated too much up to this moment, maybe just to make everybody remember these definitions. A Hilbert space, a complete inner product space. What am I going to do with it? Another definition we need is closeness. It's about a set in a metric space. A set A, subset of a metric space M, is closed if its complement is open. So with my terms, I can just write it maybe very quickly. Openness is defined in terms of the metric, the distance function D. So for example, A is open means for every element in A, I can form a ball around that element, which I call ball with center X and radius epsilon. That's going to become subset of A, and I will be able to find such a radius. So if I was able to draw a ball around a point X, centered at X, I can make it as small as I want to make sure it fits into a set A. As long as that set A is open, I can find such a ball. Well, the complement is closed. But of course, you know closed intervals, open intervals in R. So you can visualize what an open set and what a closed set is. The formal definition is no big deal. I want you to just know that you can reach the references and learn maybe the formal definition, practice with it, maybe going through an advanced calculus course. Anyways, so closeness is still something related to metric spaces. Well, the distances will be not used in the definition that I gave here, but basically it can be as an alternative definition. It can be used in an alternative definition. Anyway, so what we have learned up to this moment is closeness, a complete inner product space is called Hilbert space. And let's talk about a subspace. Now, what is a subspace of another set? It is, in this case, in this theorem, I'm going to think of a K. So if K is subset of a Hilbert space H, what I'm talking about is that any two elements, as a vector space, we talk about subspaces, two elements of X. When I add them, they will be, let's say K, two elements of K, I add them, they will be still inside K. If I multiply any element of K with a scalar, a number, like real number, it will be still in K. So it is a smaller set than H, but addition, scalar multiplication, K will be closed under these. It's like a subspace indeed. Everything is lived in K. So K is a vector space as well. K will be complete if and only if K is closed in H. Okay, so completeness and closeness are two related notions for a Hilbert space. That's how they come together. Okay. Well, shall we talk about some examples of subspaces? So if your vector spaces are three-dimensional space. What about R2, a plane? A plane will be a subspace of R3, right? Now, if you add two vectors in that plane, will they still remain in that plane? Yes. If you multiply a vector in that plane, will that be still another vector in the same plane? Yes. So this plane, any plane you want to pick in R3, will be a subspace of R3. That's that. Is it closed? Okay, closed is a bit harder to visualize. But basically all limit points will be there. So at least for our two purposes, yes. Okay, closed and open. Well, that's maybe there's more to think about it, but it's no big problem. For our purposes, more important notions here will be completeness, which is a very important property of Hilbert spaces, plus having an inner product defined here, okay? Anyways, that's something you should keep along. Now, okay, these inequalities, of course, you know very well triangle inequality. Norm satisfies triangle inequality, therefore, it will easily be converted to a distance function. Yes. What about Schwarz inequality? Well, this brings together the definition of norm and inner product. Remember, this inner product squared would be actually norm x, y. Okay, that would be, okay, that wouldn't be a norm, of course. Norm would be what? Inner product of x with itself. Take the square root, that would be a norm. So basically, we have Schwarz inequality relating inner product to the norms. But I think this you have seen several times in ordinary calculus with norm being absolute value for real line, or maybe R2, R3, inner product being a dot product. Maybe a version of Schwarz inequality you have seen for Rn before. So these are some simple inequalities, but very important basic definitive inequalities. All right, so that's there almost. I know I have been doing some technical problem solving at the first place, therefore we have lost some time, but we come to the central part of our lecture today. We want to talk about orthogonal complements and direct sums so that we can think of some operators we will call projection operators. Well, these notions you have seen in Rn and in our introductory calculus courses, so it's not going to be hard to generalize to general spaces. Well, I'm borrowing from another set of notes I have. So please disregard the section 3.3 thing, but that's the fourth slide I'm showing you today, right now. Consider a vector space M, a set, right? Made up of vectors. And delta here is a number defined as the infimum of the distances between x and all elements of M. Okay, infimum over vectors y in M, points y in M, of the norm x minus y, which is the distance of x and y, right? So y's are coming from this set. Now, is there y in M for which delta is equal to exactly the difference of x minus y, norm of the difference of x minus y, which means, is there a closest element y here? Well, with this drawing, you can see this seems like the closest element, isn't it? So here the definition is the minimum of all the distances. Is there a single y element here in M which satisfies to be the minimum distance, okay, for delta? Delta is just a number. So this minimum number is called delta. Is that delta equal to the distance of one of the elements in M? Well, with that drawing, this may seem a very superfluous question, right? I can see there seems to be a very close element right there that I'm going to call y. But this one is searching for that y, isn't it? This infimum is searching for that. Okay, let's see. Okay, mathematicians ask such weird questions. If that's an abstract arbitrary vector space, well, how do I know? Well, I don't know. So the segment joining x and y, let me look at that segment, which is just all the points between x and y. So those are the elements z such that z is a convex combination of x and y. Isn't that right? X is here, y is a point there, combine x and y. In that segment, I'm talking about elements z formed as convex combination of x and y. Is that right? Well, this is called convex combination when alpha is between 0 and 1. You know, believe me, you don't have to draw it in Rn or anywhere. This is called the segment. That's like a definition of that segment, okay? And in Rn, that's very natural. Now, if M is subset of X, so X is this whole bigger set, M is just a subset, it is convex if for all x, y in M, the segment joining x and y is in M. That's what it means to be convex, okay? Now, every subspace y of x is convex. Why? Look at the addition here. A scalar, a real number times x, plus another real number times y, they're added, right? So a vector, scalar multiple of a vector, is another vector in that subspace. A scalar multiple of vector y is another vector in that subspace. When I add two vectors in that subspace, they have to remain in that subspace by definition of being a subspace, right? Two vectors in that space, when you add them, they have to remain there. That's why I call it a subspace. So basically, convexity comes for free if I'm talking about a subspace. All right. Now, we have such a theorem here. If X is an inner product space, M is not empty, M subset of that inner product space, M is convex and complete. Let me have all these hypothesis items here, okay? All these assumptions. Then, for each element in X, there exists the closest element Y in M. It is unique, and it satisfies to be the element closest to X because the distance between X and Y, that unique element, is the infimum of all distances I would search. That Y is called the minimizing vector. Well, where is Y here? Right there. If you can see my cursor there, yeah, Y is right there. And it is a unique element, of course, depending on X. X is given, I can find the closest point Y in this subspace M of X, okay? But I had to assume several things. M should be convex, M should be complete, so Cauchy sequences should converge in M, and X is an inner product space, all right? That's that. So complete in the sense of being a subspace, of course, so M is a subspace and it is complete. Okay, by the way, I'm sorry, I didn't assume M being a subspace, okay, because every subspace of X is convex. So because I didn't assume subspace being a subspace, I just assumed convexity of that subset, Okay, so please consider this theorem as the least assumptions theorem I have at the moment. Okay, now I think it's a good time to give a little bit of a break, even if I may not continue for 50 more minutes. It's good time to a little bit relax and yeah, stay exactly on the most exciting part of the lecture. Okay, remain there. Right. So shall I just pause the share for a moment, or maybe just leave it as is if students want to have a look at it? Yeah, just stop the video for a moment, maybe. Okay, so after 10 minutes shall we be back? Shall we be back? Is that okay? 10 dakika iyi midir? 6'yı 5 geçe diyelim, 8 dakika olur mu? 7-8 dakika.
Olur.
Teşekkürler. Okay. Hello again. Merhabalar.
By the way, it's quite enjoyable. Don't think.
Thank you. I'm happy. Okay, I'm happy.
Because you give the definitions in a very constructive way. That's why we can follow easily.
I'm happy to hear that because I'm not the best lecturer maybe, but I like to draw and visualize and so on, which I haven't done very well to you up to this moment. I'm glad if you're following, at least not in a pain. Not being painful is sufficient in this case. And I'm happy that we have only one proof, which is next. That kind of makes you imagine what is going on in terms of vectors. So therefore, I'm going to prove this theorem, okay? All right, so let me give you a hint of where we're heading. We're heading at orthogonal projections. Okay, orthogonal projection. You know dik iz düşümü, right? In Rn, you know how to do this. And you know maybe the relation to dot products, inner products somehow. Remember the cosine theorem or something like that. However, it doesn't come for free if I'm talking about an abstract set M. And if you remember the example of functions x of t over an interval AB, that object is a vector. That function is a vector itself. So it's not something you can visualize as in Rn, right? Not vectors like that. It is just a function, and that function is an object that I call a vector. So therefore, please just consider this M as a set. Of course, visualize an Rn. So everything is nicely generalizable to abstract sets like this. And let's consider this theorem and its definition by visualizing in Rn, okay? So X is an inner product space. I don't know what the elements are. They are very, very abstract things maybe, but called vectors. I can add them. I can multiply them with scalars. M is a subset of that vector space. Is convex and complete, meaning Cauchy sequences in M will converge. So I can now state the result that there exists a minimizing vector y in M, which will satisfy to be the closest element to that element x if somebody gives me an element x, okay? So basically, we will try to prove this. So in the next slide, I'm going to do this a little bit larger here. Of course, I will try to visualize, although these are abstract, whatever they are. But fix a point x in this bigger vector space. And M is a subset. It is convex. There are several, of course, elements in M. And I'm measuring the distance between x and those elements. All right? Now, those distances I can show as norm x minus yn if there is a sequence of elements in M that I want to denote with yn. Okay? So there exists such a sequence which will give me a sequence of distances, delta n, and those distances will converge to the delta, infimum of these distances. Now, this is kind of, I think, reasonable to you. If delta is the infimum, it's not necessarily one of those numbers, but it's the limiting smallest number. Of course, all the distances from that sequence to x will be larger than that minimum, and they're all positive. But you know what? this there exists kind of argument here comes from advanced calculus. For a set of positive numbers which are formed with delta n, there exists an infimum. Okay, so these are some axioms we already actually accept. Okay, so if I can form a sequence closest to the border, if you like, visually, the distances will converge to the smallest distance. Okay. All right. I just don't know if there is an element here which will be the closest element. Now, what do we do next in the proof? We show that yn is Cauchy. So let me look at the distances x minus yn. Okay, when I put the norm, that will be distance. But these are the vectors. The difference of yn and x, vn vectors. So delta n is norm of vn. Everybody's okay with that part?
Yeah, I couldn't catch the why we forced the yn to be Cauchy.
We didn't force it. We will show it now. This is the next step.
But,
Good question. Okay, so I have defined Vn, the difference vector. I know the norm is the distance delta n for each one of them. Now, let me see if it is going to be Cauchy or not. We will need a proof. So I think this is a nice sampler of proofs we do in such matters in this part of the lecture, okay? So norm of Vm plus Vm, just form it. Nth element, mth element, okay? This is, what is Vn? Yn minus x, put it here. What is Vm? Ym minus x. So this is Ym plus Ym minus 2x, correct? Yes. Now, because of the properties of norm, I can factor out 2 outside if I divide everything inside with 1 over 2, of course, right? Agreed? This is just algebra. Take 2 out, divide by 2, divide by 2. All right? Now, what do I have here? This is a convex combination of yn and ym. 1 over 2, 1 over 2, right? Both yn and ym are inside convex set M. Therefore, their convex combination is also in M. Okay, now this vector minus x, okay, so a vector in M minus x, the norm, the distance of that is of course larger than delta because delta is the minimum, infimum of all these distances. So basically 2 times this norm is greater than or equal to 2 times the minimum distance, right? The infimum of all distances, delta. Okay, that's by definition, right? Remember, delta is infimum of all such distances. And here I have a y tilde minus x. That norm, of course, is greater than or equal to infimum of all these. Okay, now what do I have? Parallelogram inequality, which I did not show you, will hold with inner product spaces. So I know that it holds here as well. According to parallelogram inequality, which you may check, yn minus ym norm squared is equal to vn minus vm norm squared, by the way. So if we see yn minus ym, vn minus vm, x's will just cancel, right? If I do the subtraction, x's will just cancel. Yn minus x minus ym minus x, x's will cancel. This is the same thing as vn minus vm, if you remember that, correct? Okay, now parallelogram inequality will give me that part. Please don't go and look at the details. They all come from these red parts. Vm plus vm that's greater than or equal to 2 delta. I can put that. Minus of that will be less than or equal to. Okay, what about Vn squared plus Vm squared? That's less than or equal to delta n squared, delta m squared. Okay, because norm Vn is delta n anyway. These are just equal, not this less than or equal to, but just they're equal to delta n and delta m squared. So what did I see? Yn minus ym's norm squared is less than or equal to minus 2 delta squared plus 2 delta m squared plus delta m squared. But Yn is then Cauchy because delta n goes to delta. Delta m, of course, goes to delta. All convergence sequences are already Cauchy. So these will be just converging to delta. So 2 times delta squared, which is 2 delta squared plus 2 delta squared, 4 delta squared, minus 4 delta squared, that's a 0. So this all right-hand side converging to 0. So as n and m go to infinity, norm Yn minus Ym squared goes to 0. That means Yn is Cauchy. Okay, m is complete by assumption. Therefore, Yn must converge to an element of m that I will call y. Okay, so Cauchiness finishes here. Because of m being complete, which I use right now, Yn will converge to an element of m. Now that element I call y, and by definition of delta, y being just an element in m, y being just an element there, of course the distance of y and x will be greater than or equal to delta, which is the infimum distance. So in general, norm x minus y is greater than or equal to delta. On the other hand, I have triangle inequality. If I subtract from x Yn and add Yn, I don't change anything here, do I? X minus Yn plus Yn minus y, and apply the triangle inequality. Of course, norm of x minus y is less than or equal to norm of x minus Yn plus norm of Yn minus y. So I hope everybody can see the triangle inequality here. So you see, I'm using those very basic definitions. Being complete, triangle inequality that is satisfied by distance or norm function here. And I see that x minus Yn is delta n. What about Yn minus y? It's right here, a norm here. But I know that Yn goes to y as n goes to infinity. So the right-hand side, on the right-hand side, the second term goes to 0. What about delta n? It goes to delta. Therefore, delta n plus a sequence that goes to 0 converges to delta. Okay, in the end, what did I see? 2 inequalities. Norm of x minus y greater than or equal to delta. Norm of x minus y less than or equal to delta. Therefore, norm of x minus y has to be equal to delta. That's where we finish our proof. There exists an element y, which is going to be satisfying that infimum distance. Of course, visually I can see it should be the closest element here, and which we call actually minimizing vector in general. So what about uniqueness? Well, you can do it as an exercise. You can show that if there is another y satisfying this infimum distance to be the distance to x from itself, they have to be the same y. Okay. Well, any questions here I can repeat?
Yeah. I remember M was the complete convex set, right?
Right.
And then in this proof, we use only the property of the which is coming from the being completeness.
And convexity here.
Okay. Okay.
Right.
I try to ask that. Okay.
Yeah. Okay. In general, it doesn't have to be a subspace. I just need a convex combination to be inside them? But that's a good question. If this was a subspace, I wouldn't need convexity because this is a linear combination, isn't it? A number times one vector plus a number of times the other vector. When you add them, that's a linear combination. And a subspace is closed under linear combinations. So convexity or subspace will be sufficient. Very good. Wonderful. So that at least gives us a taste of how the proofs would be in this part of the lecture. So let me go to the second half of my presentation. I stopped sharing this one. Of course, I will share with you these notes. So let me share the second part. Part 2. Yes, right here. Okay, now we're ready to talk about orthogonal projections and complements. We have, what did we talk about? We have talked about some closest elements, right? Of to a convex subset. Okay, let me right away give you the theorem we want to discuss now. I think the rest of the lecture will be more fun because we will see the big picture. Now let Y be any closed subspace of a Hilbert space. Then that Hilbert space can be written as a direct sum of two subspace Y that I have been talking about, plus another subspace Z, which is actually the orthogonal complement of the given subspace. So I want to a little bit define those, although you have an idea of what is being orthogonal and so on. What is orthogonal? First of all, let's define orthogonal, right? Okay. Now, a vector Z in H is orthogonal to a subspace Y, okay, if it is orthogonal to all elements, all vectors in that subspace. And what is being orthogonal for two vectors? Their inner product is 0. That's that. Like dot product is 0, two vectors are orthogonal to each other in Rn, right? Similarly, if for every element of Y, that subspace Y in H, I have Z vector and inner product of Z vector and any vector in Y is 0, I write that vector Z is orthogonal to this whole subspace. Very reasonable and easy to remember and visualize, isn't it? Right? Z vector. Okay. What about this point here? I forgot to write. It is 0. All vectors are drawn from 0, aren't they drawn like that? So here's the 0 element. Every subspace has to include 0 element. 0 element is in a vector space. And this is the Z vector here I'm talking about. All right, it is orthogonal to Y if it is orthogonal to each element in Y. All right, very good. So orthogonal is good old orthogonality. We can visualize and understand. Now, what about Y perp, as I write here? What does that mean? It is orthogonal complement. And I define orthogonal complement as all Z vectors in H which are orthogonal to Y. Okay? Now, if you look at this visualization, this Z vector you can see, right? There's like a point here. This whole thing is a vector, right? From 0. This Z is orthogonal to Y, right? Are there other vectors which are orthogonal to Y? Many, right? I can draw many others. The subspace formed by those orthogonal vectors will be called Y perp or Z, capital Z. All right. So think of set of all orthogonal vectors. That set is actually orthogonal complement of y, the others. Now, this theorem, of course, we have to prove in this theorem that if I take elements from y and z and add them, I can form any element in the Hilbert space I have. Now, of course, I have to first define to you what that direct sum means. Okay, this is coming a little bit backwards now. A vector space V. For a vector space V, I can talk about direct sums. Now, for each vector in that vector space, if I can write it as sum of two other vectors uniquely. Okay, sum of those vectors, I said, those two vectors, z and y, coming from subspaces of V, capital Z and capital Y, then I can say that V is direct sum of Z and Y. And write V as Z direct sum of Y. So this sum with circle indicates this direct sum definition, basically. Maybe you would like to read it again. Okay, maybe you read for a moment, I stay and wait. Okay, so what did we do? We took each vector from space H. I can write it as one vector from Y, one vector from Z, add them. And in a unique way, I can represent every vector in H like that. Okay. Now, isn't that trivial in R2? Do I have a drawing in R2? Let me see. I don't think I have it here. But think of X and Y coordinates, right? A vector in R2, in the XY plane. I can write that vector as the sum of X coordinate, a vector in the X coordinate and a vector in the Y coordinate. This is just sum of those vectors, isn't it? Right? So R2 is direct sum of R and R. A vector from here, a vector from there, right? Sum is just on the diagonal. So R2 is direct sum of R and R. Orthogonal complements of each other. X axis and Y axis, you can show that. Okay, so this idea is generalized to arbitrary Hilbert spaces. Well, if I have a closed subspace of H, then I can write H as direct sum of Y, that subspace, that closed subspace, and its orthogonal complement. So that's our theorem that we want to cover today in this part of the lecture. Okay, so how do I come to that? Well, orthogonality lemma tells me in the previous theorem, let me take X be just an inner product space and let Y be a complete subspace. Okay, this theorem is not actually the direct sum theorem I'm talking about. I'm talking about the theorem we have just proved a moment ago in the previous part of the lecture notes. Remember, there was this closest element Y, okay? Remember that? In order to have that closest element Y, I said the subset must be convex, or I said it should be a complete subspace. Remember, we assumed M complete, M convex. Now assume Y subset of that inner product space, but not necessarily convex. Just assume it's a subspace and it's also complete. Then we have a unique Y, which is closest to a given element of X, and delta is that smallest or infimum distance. Now here I can also show that Z, the vector X minus Y, is orthogonal to that subspace. So orthogonality can be now incorporated in this whole, let me say, vision of our topics here, okay? So orthogonality is extra here proven because Y is a subspace, not just an arbitrary convex subset. It is a subspace, it is complete, then the Z, the difference of X and Y is orthogonal to Y. Okay? All right. So X is given. I find the closest element Y to the subspace Y. Now, please note that the Z vector is here because we draw all vectors from 0, don't we? This is the Z vector. I have to carry this arrow to the left on top of 0. This is the Z vector here. And yes, Z is orthogonal to whole subspace Y. Agreed? Okay. Now this can be proven. And that's another visualization of orthogonality to Y. You know what? In the previous lemma, Y is called the orthogonal projection of X onto Y. So what do I have here? X given, subspace Y given. The closest element Y here is orthogonal projection of X to subspace capital Y. All right? Okay. Well, in R3 and the planes in R3, this is really very easy to visualize. So H is a Hilbert space, remember? Y is closed subspace of H. And I can write H, because of the direct sum theorem, as a direct sum of that closed subspace and its orthogonal complement. So for every X in H, there exists a closest element to subspace Y, which I call orthogonal projection. And I can write that vector X as one element from Y and one element from orthogonal complement. Right? Now this defines a mapping. This is the part maybe we will be more formal. We will understand the function behind. There's a function, a mapping, P, which takes an element from H, maps to an element Y, which is in the subspace capital Y, that I call projection of X onto that subspace capital Y. Okay. Visualize again. I have X. Y is orthogonal projection. And I can write X as sum of vector Y and vector Z. Can you see that? Now, by the way, Z is Y minus X, X minus Y, right? So add Y and X minus Y. This will give you the vector X. Can you visualize that? Add Y and Z, which is X minus Y. This is going to give me vector X. How do I draw vector X? From 0 to that point, right? That's vector X. It's direct sum. Z plus Y will give you X. Okay, projection is something we want to focus here. P is called the orthogonal projection of H onto Y because I can apply P to every element of H. So for each X, I can apply the projection and I can find in the range an element Y in the subspace capital Y. So P maps H onto Y. All the elements will be mapped onto Y. They will be projected. I think the first one is trivial. All X elements will be projected onto Y. P maps Y onto itself. So if you start with the element in Y and you want to project orthogonal project on capital Y, basically it's the same element. It has to stay there, right? This is trivial. But what about Z? This is also very easy to visualize from this picture. If I want to project Z onto Y, it will be projected onto 0. Is that right? The projection of Z is just 0. Okay, you can show this algebraically. So algebra, meaning addition, subtraction with no geometry, is all given here, all right? So if you start with Z, project X, okay, projection of X, isn't that Y? So Px, Py plus Pz, correct? If you project is a projection operator, is a linear operator. Apply P to the left and right part of this equation. Px equals Py plus Pz, agreed? Linear operator. Px is Y, Py is just Y because it's inside. That leaves me Pz equals 0. Right? Px is Y, Py is Y. So Pz will be just 0, vector 0. So P maps Z, the orthogonal complement Y, to 0. And it is very easy to, of course, not this one. It's very easy to visualize in R3. Projection of Z is just 0 vector. Okay, these are important because this is true, not necessarily in R3 or R2. It's always true if we're talking about a Hilbert space H, complete inner product space, and Y is a subspace of H, and it is closed, then all these things work. By the way, did we talk about closedness? Yes. If it is closed, we can write all these. Did we have that? Complete subspace there, orthogonality. Yes, there when did we use closeness? You see, it was this very first theorem we spoke about. H is a direct sum of Y and its orthogonal complement only if Y is closed subspace of that Hilbert space. So all these definitions come together. Okay. I'm almost done with these, except for maybe visualizing some more here. I have 2-3 more slides, so I shouldn't be letting you go yet, but just consider Y and Z as orthogonal complements. Okay, Z is there. Now, of course, this should be orthogonal, by the way. That's Z vector. Maybe my drawing is not the best one. Now, maybe you should look at this PZ. PZ is a projection of X onto Z, okay, onto the subspace Z. But the P I'm talking about is the projection operator I have been talking about here, okay? So basically, I can talk about projection operators onto any subspace of H. So P sub Z here is just indicating I'm trying to project X onto the subspace capital Z. Okay, this is Y and Z being orthogonal complements here. Okay, so this, remember our example, which was kind of, let me say, unusual. So remember our space L2 over AB. Those are functions on closed interval AB such that they are square integrable. So their square has finite integral over AB. Now, if X and Y are two such functions, I will call those two functions to be perpendicular or orthogonal to each other if the inner product of these two functions is 0. So basically, if their integral if the integral of their product is 0, I will call these two functions to be orthogonal. So it works here. What about inner product of x with itself? That will give you norm x squared. And this is integral of xt squared, remember? So these were all in place, but orthogonality is what we show here. That's what it means. Now, completion theorem tells us L2AB can be completed. It's an inner product space and it can be completed. So we can consider the completed form of it, and we can say L2AB is a Hilbert space, just considering that completion. What about closed subspace? Let's remember what we have seen in the first hour. A closed subspace of a Hilbert space will be complete. So inner product is there, it's complete. So we will call this subspace, closed subspace, also a Hilbert space, right? That's the definition of a Hilbert space. So with more untraditional examples like that as well, we can apply everything we have learned today. Well, if you're with me still, almost there. Okay, two more lemmas that we have in this chapter. Close this. Okay, null space. If Y is closed subspace of Hilbert space, then the orthogonal complement will be null space of projection operator. Well, what does it mean to be null space? It means for an operator, a null space means if I take an element from that space, it is going to be mapped to 0. Well, isn't it like that? Projection of Z, if I apply the P to Z, the projection will be 0. Don't take this PZ. I'm just talking about this projection operator. Okay, it is this picture here. So if I project Z onto Y, right, that's capital P operator, it's always going to give me 0. So all these vectors are in the null space of P. If you remember null spaces from matrices, that's what it means to be null space, right? Apply the matrix to a vector. If it gives 0, that vector is in the null space. If you remember eigenvalues, eigenvectors, when you had to find those, you learned the definition of null space. So that Z, or which is Y perpendicular, is the null space of P. Okay, that's very easy to show because we already know PZ is 0. Okay, don't read all these things, but let's look at this lemma. If Y is a closed subspace of Hilbert space H, then this is very easy to prove too. And Y equals Y per perp. If you look at the orthogonal complement of C, that's going to bring you back to Y. So orthogonal complement of Y is Z. Z orthogonal complement will be Y. It will be back. Well, all these are possible just because Y is a closed subspace. So closeness helps there, which we haven't really used much in our proofs. But believe me, this is a very crucial definition right there. Okay, so you can write H as Y direct sum of Y orthogonal complement, or for Y orthogonal complement, you can write Z. And remember that Y is Z orthogonal complement. So both are fine. Therefore, PZ is legitimate to write. So I can do a projection on Z as well, because Z is also a closed subspace of H. We can show that. Anyways, I hope this gave some taste of orthogonality to you, but let's visit as in our final slide, probability. I'll be back to that. Any questions about orthogonality? Maybe it's nice to remember your definition of null spaces and so on with matrices, because matrices actually represent linear operators. Well, they represent linear operators in any abstract vector space, so they're good, okay? So let's visit probability, something you have studied for the whole semester. Where does orthogonality, etc., go and fit to? Well, it will fit into conditional expectation. You haven't really covered that much, but this is where Professor is heading to. Süleyman Hoca wanted me to cover these topics because the next will be conditional expectation. Well, let's remember our ordinary expectation. Now, in relation to convergence in L2, that's something I'm going to define. Let me remember random variables. So random variables are functions from our probability space omega to real numbers, possibly real values. Okay, now omega is an abstract probability space, suppose with a probability measure P. So the value is R, extent of omega will be different for each omega. Omega is like our outcome, right? Flipping coins. Extent of omega will be a number. Now, I'm thinking of a sequence that I'm going to use a little bit later. Therefore, I have this subscript n, but don't bother yourselves with n at this time. One of those x random variables, okay? Now, xn or x in general is called to be in the space L2 of omega if expected value of xn squared is finite. Okay, I'm talking about real valued random variables here. So x is a real valued random variable, or xn here, one of those variables in a sequence of random variables. If it has finite second moment, I can say that it is in L2 omega because I can talk about now, similar to our previous example in L2 functions over AB. This time I want to define inner product a little bit differently. Not with respect to Lebesgue measure dt, okay? But I want to think of an integral with respect to our probability measure. So xn squared here in this case is integrated with respect to our probability measure. And if this is finite, I can form an inner product space, because I can define inner product of two random variables as expectation of their product, okay? X times y probability, that's expectation. So this is expectation of xn squared. Expected value of x times y will be x times y p d omega over the set omega. What about L2 norm? That will be square root of expected value of xn squared. Okay. Now, you can find L2 convergence in Süleyman Hoca's book in Financial Mathematics. If we say that a sequence xn converges to x in L2 if the norm of the difference of xn and x converges to 0 as n goes to infinity. Okay, so this is very much in analogy with our definition of inner product. Where are we? Right? In this L2 functions. In this case, I'm not talking about Lebesgue measure, but probability measure. I know how to integrate with respect to probability measure. This type of inner product is well defined. But when I do such integrations, I call them expectation, don't I? Simply. So expected xn squared is this one. Expected xy satisfies the properties of being an inner product. And convergence in L2 will mean the norm in L2 will converge to 0 as n goes to infinity. All right? So orthogonal projections will follow. If I can talk about inner product, if I can talk about completeness, okay, completion, by completion theorem, we can show these. We can talk about orthogonal projections, and those projections will actually lead you to conditional expectations, okay? So how am I concluding this lecture? I'm concluding with lots of question marks, probably. If you go and read the relevant parts in Üstüner's book, which is available to participants of this lecture series on the web, you will find the relevant places, conditional expectation chapter. That will be following on top of all these inner product ideas, projection ideas, and you will be seeing that conditional expectation is really a powerful tool in applications, but it has a very powerful basis coming from functional analysis as well. You can also read the part related to martingales. So these are chapters which follow, towards the end of the book. Well, that's all I want to say. And I will sure make this set of notes available to you that you would be able to upload, I guess. Evet, sıra sizde. Sormak istedikleriniz,